This video is part 1 of the video review for Unit 3, Chemical Reactions. In this review video, we're going to be looking at the different types of chemical reactions, and then later in part 2, we are going to look at aqueous solutions and solubility. So first of all, let's tackle the question, what is a chemical reaction? So a chemical reaction is the transformation of one or more substances into different substances. Let's look at the classic car example. So in order for a car to be fueled, we are going to use gasoline, which is an octane. And in the engine of a car, octane and oxygen are combined to create energy. These two compounds, octane and oxygen, are called the reactants in this chemical reaction. The products of the chemical reaction are carbon dioxide and water. In order to make the products, octane and oxygen combine together and rearrange to form these new substances. Energy is a byproduct that's created. Its energy is not a compound and it's not matter. But the products are going to equal up to what was put in. So carbon dioxide, the carbon would come from the octane and the oxygen would come from the oxygen. And then the water, which is H2O, again, the oxygen in the water would come from the oxygen, and the hydrogen would be part of the octane. You have to remember the law of conservation of mass here, that nothing new is created and nothing is destroyed. So the atoms from the octane and the atoms from the oxygen are rearranged to create these new compounds. Let's look at another example of a chemical reaction. In this example here of our classic baking soda volcano, we have baking soda, which is sodium bicarbonate, reacts with vinegar, which contains acetic acid, to form carbon dioxide gas and water, plus sodium acetate. In this chemical reaction, the sodium bicarbonate, which is the baking soda, and the acetic acid in the vinegar are the reactants that recombine to create the products, which in this case are the carbon dioxide gas, the water, and the sodium acetate. Heat is also released in this chemical reaction. If you are to count up the sodium atoms and the carbon atoms, the hydrogen atoms, and the oxygen atoms in the reactants, you should have the same amount of atoms in the products. Because of the conservation of matter, you need to have the same amount of atoms going in as the same amount of atoms going out, and they have to be the same types of atoms because atoms don't change after a chemical reaction. They just recombine to form different compounds. We witness chemical reactions around us every day, but some of those things that we witness that we think are chemical reactions are actually not chemical reactions. It's not that something new has actually been created from the reactants. It's just that there is a change in state. We still have the original thing, it just looks different. So how do we know when an actual chemical reaction takes place? Well, first of all, you absolutely have to have a new substance being formed. And you have to remember that change in state is not a chemical reaction. So let's look at some evidence of chemical reactions. When we're talking about evidence of chemical reactions, there's a few things that we have to keep in mind first. First of all, changes occurring at the atomic and molecular level determine whether a chemical reaction has occurred. Therefore, you have to have a change in the atomic composition of the product for there to have had a chemical reaction occurred. So the atomic level is really important. Has the composition of the substance changed at the atomic level? The only way to really know if you have a chemical reaction is through a chemical analysis. Some chemical reactions can occur without any obvious signs. An example of something that looks like a chemical reaction but is not is boiling water. So boiling water forms gaseous steam, but both the water and the steam are composed of water. So the water in its liquid form and water in its steam form is not a chemical reaction because liquid water and gaseous water are still composed of H2O, 2 hydrogens to 1 oxygen. So the composition is the same. So no chemical reaction has taken place. This is just an example of a change in state. So if you don't have the benefit of being able to do a chemical analysis, what are some of the clues that a chemical reaction has taken place? On this side of the slide, I have examples of different forms of evidence that might suggest that a chemical reaction has taken place. First of all, a color change. If you get a change in color, so maybe a liquid going from having no color to a color would be an example of evidence of a chemical reaction. The formation of a solid in a previously clear solution, that solid is called a precipitate. So the formation of a precipitate would be evidence of a chemical reaction. The formation of gas when you add a substance to a solution. So you see gas bubbles when you add two substances together. That would be evidence of a chemical reaction. The emission of light. So if you think about when you crack a glow stick and then suddenly it lights up, and that energy that's being released is evidence that a chemical reaction has taken place. And the emission or absorption of heat. So the emission of heat would cause things to warm up, and the absorption of heat would cause things to cool down. So when you add two substances together and it heats up or it cools down, think about those hot packs that you put into your mittens, or even cold packs, then that would be an example of chemical reactions. But again, the only way to truly know if a chemical reaction has taken place is if you do a chemical analysis and you look at the compounds in the reactants and you look at the compounds in the products, and if the atoms have rearranged to create new compounds, then you know for sure that a chemical reaction has taken place. Chemical reactions can be written as chemical equations, and that's the next part of our video, is how to write chemical equations. First of all, a chemical equation involves the reactants on one side and the products on the other, and then an arrow to show that a chemical reaction has taken place. The reactants and the products are given as a compound formula, showing the number of atoms for each element that combine to create the compound. Oftentimes, the state of the compound is included along with the formula. So in this case here, we have methane and oxygen, and they are both in gas forms, and they combine to create carbon dioxide and water, and they are both in gas forms as well. The different states that we can show in a chemical reaction are our gas, liquid, solid, and then something we call aqueous. And whenever you see the AQ abbreviation after a chemical compound formula, it means that this is an aqueous form, which indicates that the substance has been dissolved in water. Now, when a substance is dissolved in water, the mixture is called a solution. But this is not a chemical reaction in and of itself. So whenever you dissolve something in water, let's think about salt. When you dissolve salt in water, you can get the salt back by evaporating the water. We saw that in the mixtures lab. If you can get the substance back just through evaporation, then that's not a chemical reaction. So dissolving in itself is not a chemical reaction, but we can say that a substance is in solution by putting an AQ after the compound in a chemical reaction. Now, in this equation with states, if you were to count up the number of atoms for each of the elements, you would see the following. Carbon has 1 atom. Hydrogen has 4 on the reactant side, and oxygen has 2. On the other side, we have carbon showing 1. We have oxygen showing 3 because we have 2 in the carbon dioxide and 1 in the water, and hydrogen we have 3. And if you look side by side, I mixed up the O and the H here, but 1 carbon, 4 hydrogens, 3 hydrogens, 2 oxygens, 3 oxygens. We don't have the same number of atoms that we began with. And that's a problem because it means that our equation defies the law of conservation of mass and conservation of matter as well. So we have to balance the equation. And the way that we balance the equation is by adding coefficients. A coefficient is a number that you put in front of the formula that multiplies everything in the formula. So in the balanced equation, they put a 2 in front of the oxygen and a 2 in front of the water. Let's look at how that changes the number of atoms in the reactants and the number of atoms in the products. So for carbon, we still have just 1 atom here. For hydrogen, we have 4. And oxygen, with the 2 now as the coefficient in front of the oxygen, 2 times 2, we multiply, that's going to give us 4 oxygens. On the reactant side, we have 1 carbon. Hydrogen, we have a coefficient of 2 in front, so 2 times 2 gives us 4 hydrogens. And in terms of oxygen, we have 2 oxygens here. That 2 is going to now be applied to the oxygen as well here. So that's 2 oxygens in the water. So we're going to have 4 altogether. You can see that by balancing the equation, we have now balanced out the number of elements in the reactants with the number of element atoms in the products. And that now agrees with the law of conservation of matter and mass. Given a base chemical reaction, we want you to be able to balance it by putting in the correct coefficients to balance out the number of atoms in the reactants and the products. And there's some basic balancing equation rules that will help you to balance an equation quickly and efficiently. And by following these, you'll find that you won't have to use as many steps or retry equations if you follow these rules. Now, the first rule when you balance equations is always to leave pure elements to the last, especially hydrogen and oxygen. So if you have any compounds that are pure, you want to leave those to the end. Secondly, balance elements that only occur once in a compound on both sides first. Balance your metals before your nonmetals, and balance your polyatomic compounds as a unit. I'm going to show you an example that highlights each of these rules so that you have an example to go by, and practice makes perfect. So I have attached a question sheet or a balancing sheet with lots and lots of problems just to give you lots of practice with balancing chemical equations. So the first example that we have is write a balanced equation for the reaction of solid aluminum with aqueous sulfuric acid to form aqueous aluminum sulfate and hydrogen gas. And you can see right away that formulas for each of these compounds aren't given. So you have to draw upon your new knowledge of writing formula to create the chemical equation first for this, the skeleton equation, and then you're going to use coefficients to balance the equation. So let's identify the reactants. First of all, solid aluminum is a reactant, and it's reacting with aqueous sulfuric acid. And these are going to transform into the following products: aluminum sulfate, and I'm going to give myself a little bit more room here. Plus the other product, which is hydrogen gas. There we go. A little bit more room. There we go. So there is the chemical equation. We've added some symbols to our reactants, and we've added the arrow to show that we're having a transformation into for the chemical reaction, and we've added another add sign here. Our next step is to create our equation. So first of all, solid aluminum means that it's only made up of aluminum atoms, and aluminum, when it is a solid, is just at a ratio of 1 to 1. It's not a diatomic molecule, so we don't need to have a subscript here of 2. We just leave it as aluminum 1. Then we're going to add it to aqueous sulfuric acid, and I should put an S here to show that my state of the aluminum is solid before I move on to aqueous sulfuric acid. So for aqueous sulfuric acid, I do need to know my formula for my acid, and because we have the IC as our suffix for sulfuric, then that means that we're looking at sulfate as our polyatomic ion for this acid. So it's going to be hydrogen plus sulfate. And the formula for sulfate is SO4. Sulfate has a charge of 2 minus, and hydrogen has a charge of positive 1, so that means that they're going to come together at a 2 to 1 ratio, remembering that we bring down our charges so that we know how many atoms are coming together for each. So once we have our subscripts identified, I'm going to add AQ to show that the state of my sulfuric acid is aqueous. Next, I have aluminum sulfate, and the aluminum sulfate is going to be my aluminum coming together with my sulfate. And sulfate has a charge of -2, and aluminum has a charge of +3, so that's going to come together with 2 aluminum and 3 sulfate. See how I put the sulfate in parentheses and then added 3 as the subscript, and again this is in aqueous format. So aqueous aluminum sulfate, and then lastly I have hydrogen, and that's in gas form. But remember, hydrogen is a diatomic molecule. It's part of that Hofbrinkel acronym that we use to remember the diatomic molecules, and hydrogen is one of them. So that means when it's by itself and it's a pure substance, it's going to come together 2 atoms to create that one hydrogen gas molecule. Now that's step 2, where you write the formulas and you make sure that you have the right subscripts for those formulas. The next thing that we want to do is we want to list all of the elements and how many atoms there are in the reactants and in the products so that we can do our last step, which is to balance them out using coefficients. So following the balancing equation rules, we want to leave pure elements to the last, and the only pure element that we have is hydrogen. So we're going to leave that to the last on both sides to balance. So I'm going to count those last. Also looking at my balancing rules, it says to balance my polyatomic compounds as a unit, and I do have the polyatomic compound of SO4. So I'm going to do those together, and then that leaves aluminum. Whoops, and aluminum I will leave I will do at the first part of it. So looking at aluminum, on the left side of my reactants, I have my aluminum here. There's no subscript, but I know that to be 1. And then on my other side, I have aluminum here, and there's only 1 aluminum on my right, but there are 2 as my subscript. So 1 atom to start with of aluminum creates 2 at the end. My sulfates, on my reactant side, I just have 1 unit of that. And on my product side, you can see that I have a 3 as my subscript on the outside of that parentheses. So there's 3. And then for my hydrogen, on my reactant side, I have 2. And then on my product side, I have 2 as well. So you can see that my hydrogens are already balanced out. It's my aluminums and my sulfates that I have to look at. Now, as I balance each of these, and I wanted to do aluminum first, then sulfate, then hydrogen, it might affect the ones as they go down. But then as I complete the balancing, hopefully it will all work out. So I'm going to need a little bit more room here. So looking at our aluminum, we have 1 aluminum on the left and 2 aluminum on the right. So to fix that, I can only use coefficients. So I'm going to put a 2 in front of the aluminum here, and that changes from having 1 aluminum in the reactants to having 2. And it doesn't affect any of the other compounds. It now looks like my aluminums have been balanced. Looking at my sulfate, I have 1 sulfate on the left and 3 on the right. Again, I can only use coefficients to balance, so that means I have to put a 3 in front here. Now I'll have 3 sulfates, but you can see that it also affects my hydrogen, because that 3 not only goes to my sulfate, but it also goes to my hydrogen. The coefficient is the only thing you can add. I can't add subscripts. So 3 times 2 means that I now have 6 hydrogen. But my sulfates and my aluminum are now balanced. That leaves me with my hydrogens. I have 6 hydrogens on my left, 2 hydrogens on my right. If I want to change my hydrogens on my right to be 6, I'm going to put a 3 in front of my hydrogen here. That's going to give me 3 times 2 hydrogen, gives me 6 hydrogens, and now all of my elements have been balanced, and I have the same amount starting as I do completing the chemical reaction. So those are the steps that you take. You won't always have to write the formulas. Oftentimes the formulas for your reactants and your products will be given, and you will need to just do the balancing. But it's best to follow these rules for balancing, because you can see that I did, as I went through each of these, when I did aluminum, things underneath can start to change, and what you don't want to have happen is to get all the way down to the end and then have that change something that you already balanced, because then you have to kind of start all over again, and it can get compounded if you don't do it in the right order. So let's look at some more examples. So in example 2, we have hydrochloric acid combining with oxygen to create new products, which are water and chlorine as a gas. Our first step in balancing equations is always to list our elements, and I like to list the elements in the order that I'm going to balance. And true to the chemical reaction rules, I want to leave any pure elements till the end. So oxygen would definitely be a pure element. And so I'm going to do that on either side. And then hydrogen is something that I'm also going to leave to the end, because you always want to leave hydrogens and oxygens, and that's a non-metal, and you want to do your metals first. So I'm going to put chlorine first. So that's really why I chose that. I'm going to balance my chlorines, I'm going to balance my hydrogen, and then I'm going to leave my my pure elements, which in this case is oxygen, to the very end. So counting this up, first of all, looking at chlorine, chlorine doesn't have a subscript, so I assume it to be just 1. Hydrogen on my product side, again, doesn't have a subscript, so I assume it to be 1. And oxygen has the subscript 2, so that means there's going to be 2 atoms in that. On the product side, I have 2 chlorine, looking at that subscript. I have 2 hydrogen, and my oxygen does not have a subscript, so I assume it to be 1. Sometimes you'll do this and they will balance out right from the start and you don't have to add any more coefficients, but as you can see here, they aren't adding up. So it's now my duty, my job, my task to balance them out, and I am going to start with chlorine. So if I have 2 chlorine on the product side, I need 2 chlorine on the reactant side, and again, can't stress this enough, I can only add coefficients. I can't just put a 2 as a subscript to chlorine and have that work. I can only do the coefficients. So when I put the 2 in front of the hydrochloric acid, that's going to give me 2 chlorine, but it's also going to change my hydrogen count. So now I have 2 chlorines and I have 2 hydrogens. But my chlorines have balanced out, so I've done that. Now looking at hydrogens, oh, isn't that nice? My hydrogens also balanced out by doing that, so that's a nice surprise. And then that leaves me with my oxygen. Now my oxygen, I have 2 over on my products, my reactant side. I only have 1 on my product side, so I'm going to put a 2 here. When I put a 2 there, I knew I was excited for no reason, too early. That's going to change my oxygen to 4. And it's going to change my hydrogen to 4 and my oxygen to 2. So I'm not quite out of the woods yet. My chlorines are still okay. My oxygens are at 4 and 2. So what I'm going to do before I do, even though my oxygens have balanced out, it's my hydrogens that aren't quite there yet. So what I have to do actually is change my 2 here to a 4 in order to balance out my hydrogens. So you keep on going, don't worry if things change, just keep on going and try and work out with the balances. So I had a 2 in front of my hydrogen, but now I'm going to put a 4. That's going to change some things. I'll now have 4 hydrogen, but I'll also have 4 chlorine. So that's not the best, but that's okay. I'm going to go back up to my chlorine because my chlorine is now unbalanced. I have 4 on my reactant side and 2 on my product side. So I'm going to put a 2 here. Why am I putting a 2? Because 2 times 2 will give me 4. Now my chlorine is balanced. I have 4 chlorine and 4 chlorine. My hydrogens are balanced at 4 and 4, and my oxygens are balanced. So that took a little bit more to balance, but it worked out in the end. So don't be too worried as you're balancing that something you did before unbalances something you did afterwards, and if you have to go back, then you have to go back. That's okay. Let's look at another example. So in our next example, we have bismuth chloride, it's a hard one to say, plus hydrosulfuric acid, and those are our reactants, and then they become our new products, which is bismuth sulfide and hydrochloric acid. So the first thing we're going to do is list the elements for each one. So looking across, we want to leave our hydrogen to the end, because that's always a good thing to do, leaving hydrogen and oxygen to the end. We want to do any metals first, so that's going to be bismuth on both sides, and we will do chlorine next, and then our sulfur, so leaving our non-metals to the middle. Then what we want to do is we want to count up how much we have on each side. Now, that's bismuth, so this is an I and not a 1. Bismuth does not have a subscript, so that means that there's only 1 on the left-hand side, and on the right hand it has a subscript of 2. Chlorine has a subscript of 3 on the reactant side, and on the product side we just have 1, so it's going to be 1. Sulfur on the reactant side doesn't have a subscript, so we say that it has 1, and sulfur on the product side has a subscript of 3. And then hydrogen, there are 2 on the reactant side, and on the product side there is 1. And looking at our products, our reactants and our products, you can see that we don't have a balancing of the elements. So we're going to start with bismuth first. Bismuth on the product side has 2, so in order to get 2 on the reactant side, we're going to put 2 as the coefficient, only allowed to change the coefficients. That's going to change our bismuth count to 2. It's also going to change our chlorine count. 2 times 3 is going to give us 6. Our next element that we are going to balance is chlorine. We have 6 chlorine on the reactant side, 1 on the product side. So we're going to use the coefficient 6 to balance that out. 6 times 1 gives us 6 chlorine, but it also changes our hydrogen count. 6 times 1 is going to give us 6. So far we're doing a good job. Looks like we've balanced out our bismuth and our chlorine, but that's not to say when we now balance out our sulfur that we might need to go back. So we have 3 sulfurs on our product side, so that means we need 3 sulfurs on our reactant side. So I'm going to use the coefficient 3. 3 times 1 gives us 3. This also changes our hydrogen. 3 times 2 gives us 6. And look at that. By balancing sulfur, we were also able to balance hydrogen. So to double check, just to make sure that all of my elements are balanced on each side, bismuth has 2 on each side, chlorine has 2 on each side, sulfur has 3 on each side, and hydrogen has 6 on each side. So all of the elements balance out. So I have confidently balanced the equation with these coefficients. Now my next example 4, is going to be a little bit more complex, and you'll see as we go through the balancing why it's more complex, but I don't want to give it away now. Let's just go ahead like this is a regular balancing equation problem. We have iron chloride, we have ammonium sulfide are our reactants, and then they're going to recombine to become iron sulfide and ammonium chloride. So they're switching their nonmetals. So the first thing we're going to do is we're going to list which ones we are going to do first and which ones we're going to do last. Now we always want to do the metals first. So that's going to be our iron on either side, and that's it for our metals. NH4 is ammonium, which is a polyatomic ion. So that is considered to have a positive charge. So we'll do that after iron. And because it is a polyatomic ion, we're going to keep that together. And then we will leave our nonmetals to the last. So that's going to be our sulfur and our chlorine. So following the balancing rules, making sure we do our metals first, nonmetals after. If there were any oxygen or hydrogen, we would leave those till the end. And if there were any pure elements, we would also leave those to the end as well. But we don't have any pure elements all by themselves, so we're not going to worry about that. So the next thing is to count everything up. Iron doesn't have a subscript on the reactant side, so we know it's to be 1. On the product side, we have it that there are 2 irons. In terms of the ammonium, on the left-hand side, there's 2 of those. Outside of the brackets tells us that there are 2. And then on the reactant side, sorry, the product side, there are no brackets, so we just say that there is 1 ammonium on that side. Sulfur on the reactant side doesn't have a subscript, so we assume it to be 1. And sulfur on the product side, there's a 3. And then chlorine on the reactant side, there's a 3. And chlorine on the product side doesn't have a subscript, so we say it to be 1. Now our first job is to balance the iron. So if we have 1 on the reactant side and 2 on the product side, then our coefficient that we're going to put here is 2. That's going to give us 2 iron, but it's going to change our chlorine. 2 times 3 gives us 6 chlorine. So now, so far, our irons are working out. Our next step is to do our ammoniums. And ammonium, we have 2 on the reactant side and only 1 on the product side. So I'm going to put a 2 in front. That's going to give me 2 ammonium and 2 chlorine on that side. Next, I'm going to do my sulfurs. I have 1 on my reactant side, 3 on my sulfur side, so I'm going to put 3 here. 3 times 2 gives me 6 ammonia. See, 3 times 2 gives me 6, so that changes up my ammonia. And then I have 3 times 1 gives me 3 for my sulfur. Now that messed up my ammonia for my product side, so I'm going to need to change that because I have 6 ammonia on my reactant side. I'm going to need 6 ammonia on my product side. So that changes this to be 6, but it also changes my chlorine to be 6. And just by doing that, I was able to have my chlorines balance. So the big thing here is first to make sure that you keep your polyatomic ions together, that you do your metals first, and the ammonia is a metal as well because it has a positive charge, so it's considered a metal compound. So we're going to do those first, and then leave your nonmetals till the end. And you can see that my iron, my ammonium, my sulfur, and my chlorine now balance correctly. So here's one that doesn't seem too complicated on the onset. We have hexacarbon, hexahydrogen combining with oxygen gas creates new products, which are carbon dioxide and water. But noticing that we only rearrange the carbon, hydrogen, and oxygen molecules to create these new compounds. So in balancing this, I'm going to do, they're all actually non-metals. So carbon, hydrogen, and leaving my oxygen to the end because it is shown here as a pure element. And carbon, hydrogen, oxygen to the end on that side. So the first thing that I want to do is write down what I have on either side. And oxygen, you can see, is split. It's in both. So that's going to be 2 in the carbon dioxide, 1 in the hydrogen, so for a total of 3. So you have to be aware of that sometimes you can have an element that occurs twice on one of the sides, and you're going to have to total up the number of atoms for that element altogether. So starting with carbon, I have 6 carbons on my left, so that means I want to have 6 on my right, so I'm going to put a 6 as my coefficient in front of carbon dioxide. That's going to change my carbon dioxide to 6 carbons, carbons to 6, but it's going to change my oxygen to be 6 times 2 is 12, plus 1 is going to give me 13 altogether. I am going to leave my oxygen to the end, so my next thing I'm going to do is try and balance my hydrogens. I have 6 hydrogens on my left, I have 2 on my right, so I'm going to put this as 3 as my coefficient, and 3 times 2 give me 6 this way. This 3 also changes, my oxygen here, so I now have 3 here. So I had 12 oxygen, with the 6 times 2 gives me 12 oxygen, plus the 3 oxygen from my hydrogen are going to give me 15 oxygen altogether on my right hand side. The oxygens are the final balance that I need to do here, and I have 15 on my right but only 2 on my left. There isn't a whole number that I can multiply 2 by in order to get 15. If I multiply it by 7, I'm going to get 12. If I multiply it by 8, I'm going to get 16. So if you get an odd number, it's really hard to pick a coefficient that's well, you can't find a whole number. So what I say in this case is to instead put in a decimal just for the time being. If I put 7.5 in, 7.5 times 2 is going to give me 15. I'm not allowed a decimal in my coefficient, but I can fix that. But for the time being, you can see that I have balanced my carbon, I now have my hydrogens balanced, and I now have my oxygens. Make sure that everything's balanced, even with the decimal as your coefficient, before you do the last step. The last step is this. We need to change this decimal coefficient into a whole number. And when you have a decimal coefficient, you multiply it by a number to make it whole. So in this case, I can multiply 7.5 times 2. That's going to give me 14 oxygen. And whatever I multiply, 15 oxygen. There we go. 15 is going to be my coefficient for O2. But whatever I do to that one, I'm also going to do to the coefficients in front of all the other compounds, just to make it even and equal. So what that means is that I'm going to have 1 times 2 is going to give me the coefficient of 2 in front of C6H6. 2 times 7.5 is going to give me that coefficient of 15 that I talked about before. 2 times 6 is going to give me a coefficient of 12 in front of the carbon dioxide. And 3 times 2 is going to give me 6 in front of the water. So my actual coefficients to balance this out are going to be 2, 15, 12, and 6. And the reason why is because I can't keep this 7.5 decimal that I ended up with. So I had to multiply it by 2 to make it the whole number 15. And if I multiplied this by 2, I had to multiply everything else by 2 as well. So you will come across some problems where you might have to use a decimal coefficient just in the beginning to do this, just in the interim, and then you can fix that at the very end. Once everything balances out, you can then go through and multiply that decimal to make it a whole number. But just remember, whatever you multiply it by, you also have to multiply all the other coefficients by that as well. That is balancing equations. Up next, we're going to look at different types of chemical reactions, and that's going to be in part 2 of this video review series for a later time. Thanks for watching.